Hello everyone, this is a video lecture to make up for the day we lost on Monday due to the snow. I'll begin with the machine learning slides that Dr. Linus provided me to cover clustering and dimensionality reduction, and then we'll jump into coding right afterwards. So just kind of getting started here. There are three very common machine learning tasks. These include classification, regression, and clustering. I believe you guys have talked about classification and regression, but just kind of giving a brief review on those. In classification, this is one example, we have some features that we're plotting our instances with, and then we have the label for those. So for instance, here we have the information that these are not spam emails. We have the information that these are spam emails, and based on those true labels, we can actually draw a very clear decision boundary and separate spam and not spam emails. For the regression task, we have some number of features here. We have a true response variable for price in this case, and then we actually just want to find a line that best fits the data that we have given our labels. And these are both called supervised learning tasks because we have information, or we have the true label. However, clustering is a little different because we don't necessarily have the true information. We call these unsupervised tasks. Now, here we actually have, again, some feature axes here, and we have several different distinct groupings. Now, the idea is that in clustering, we don't necessarily want to go through and pick and choose which ones belong to which instances. We want to have an automated way to choose which clusters these instances belong to. And in this case, it's pretty trivial. We're going to have cluster 1 here having 4 instances, cluster 2 cleanly, having 5 or 6, and cluster 3 having 5, not 5. And so the idea here is just to try and find some patterns in the data based on the properties of the data. We'll kind of talk more about how we do that, but getting into some more machine learning tasks. On the left, we have some dimensionality reduction, and on the right, we have reinforcement learning. So on the left, the idea behind dimensionality reduction is that we want to take a lot of information and we want to compress it down, or rather project it down and keep as much information about the data as possible. So here we have a cube in 3 dimensions that has about 1,000 positions worth of data points, right? Some crazy amount. When we project that down to 2 dimensions, we can see we have about 100 positions left. What we're trying to do is maintain as much information about this space as we can, while also reducing the size of the data. We can also reduce it further to a one-dimensional representation of the data that only has 10 positions. Again, this is maintaining as much information about the data as possible, but at the same time, reducing it a significant amount. And so we'll talk more about how we do that and maybe why we'd want to do that as well. And then reinforcement learning, we won't go too much into this, so I'll give a longer explanation. The idea behind reinforcement learning is that we only give an agent the ability to move in the space. And so, for instance, in this space, move left, right, down, and up are its 4 options. Now here, we don't want to program in explicit rules. That's the whole idea of machine learning. We want it to learn rules from data. So we're going to have an exploration and an exploitation trade-off. Now, exploitation is going to be the robot exploiting routes, paths, strategies it already knows that work or get some reward. Exploration is trying new things that, although they may work worse, the robot now has knowledge about that method or that attempt. So if we take the example of why this is necessary, of this path right here. Now, let's say the robot moves up, finds a very low reward, moves up, finds a very low reward, and it's stuck. And it doesn't ever try to explore because its only exploited action is up, and that's all it knows. However, if we add an exploration component to this robot, we can easily find higher reward states that the robot can take with different actions that it's now explored. Again, we didn't tell it to try and take right. We just gave it a variety of options and said, explore until you find a good strategy, then exploit that. And essentially, this is the idea of reinforcement learning, giving an agent what moves or what valid actions it can take, and then letting it explore the space until it finds an optimal solution or near optimal. And actually, Dr. Clune has a video or two at a conference where he talks about the folly of the exploitation and trying to just meet accuracy requirements. And it's a very interesting talk. If you're interested in reinforcement learning, he gives a very good talk that's a good introduction to it. There's also a significant amount of information out on the internet, so please research that if you're more interested. But kind of getting back to our topic today, let's start with clustering in a more in-depth way. So clustering simply aims to automatically group instances in some unique way. So here we can see that we have some blue dots because they're all very close together. Green dots are all very close together, and the red dots are all very close together. Now, the idea here is that this is a partially clustered data space here, and we'll continue clustering by adding these black points actually to these different clusters. So for instance, it's very, very easy to see that these black points should go to the blue cluster here. These black points should go to the green cluster here, and these black points should probably go to the red cluster here. However, where it gets more difficult is, say, with these ones right through here. Which points or which clusters should these be assigned to? And this is where we need more explicit rules, and this is kind of where clustering is a challenging but interesting field as well. Because grouping really does depend on the chosen metric. So, for instance, if we look at this cast of The Simpsons characters, what's a natural grouping among all of these objects? Well, it is subjective ultimately. So, for instance, one clustering could be we're clustering the Simpsons family versus the clustering of the Simpsons employees or school employees. Another clustering could be we're just clustering the females and the males out of this group. And it does become a question of which one is better, which one is worse, and it may just depend on your goal. Ultimately, maybe you would like to know information about the cluster of females and males. Maybe you would like to know information about the clustering of a family versus an environment. And so this is an interesting problem that a lot of clustering runs into. However, we'll start off with a pretty basic and very, very widely used algorithm still called k-means clustering. So k is just going to be our number of clusters, and it's a hyperparameter. So here we have some input data, and we're going to randomly choose 3 points. Again, because we're choosing k equals 3, we're going to choose 3 points, and just totally randomly. Now, based on these points that we've chosen, we've now assigned this one to the black group, the red group, and the blue group. We're going to find that the average is just that point. Now that we have the average, or the centroid as it's called, we're going to assign the data points to their closest centroid. So for instance, the red points were all closest to this centroid. The black points were closest to this centroid, and the blue points were closest to this centroid. Now that we have a clustering assignment for every point, what we're going to do is recalculate the centroids for each one of these clusters. So you can see here, we now have this cluster centroid from this picture, this cluster centroid from this picture, and this cluster centroid from this picture. Based on those new centroids, we are going to reassign the data. So you can see here, it's probably the most obvious for the black points. Based on this centroid, which is from this iteration, we are actually going to reassign all the points. And we actually are starting to see that this is becoming a very nice little grouping. This is becoming a nicer grouping, and our red points are still doing okay on their groupings. And when we keep doing this, we'll actually see that these centroids, again, these are going to be from our last iteration. You can see that the blue center has gone up to about here, and that the black center is about, here now, right, based off this assignment. And now that we've got the new centroids, we're going to reassign to the nearest centroid, and then we're going to recalculate the centroid. And so here are the centroid locations for each one of our clusters in this data. And when we actually go to try to recluster these to figure out what points are close to what centroids, at this point we're going to find out that there are no changes. It's at this point that k-means has absolutely converged. And actually this is a guaranteed result for k-means. It will always find a convergent result where no instances will change cluster assignments. Now you may have some questions about, are the cluster assignments going to be always static, always the same? Are they always going to converge to the same point? And the answer is no, they won't. So if we go back to our seed point selection, imagine we had an outlier out here, and this was chosen as our initial starting point. Now, maybe it would pick up this point or something, but I kind of doubt it. I kind of suspect that it would be only closest to itself, and we have two other starting points through here. A very realistic final clustering then becomes this being one cluster out here, this anomalous point, this being another cluster, and this being a cluster. And this is a danger with using the k-means algorithm. It's very, very sensitive to outliers. And actually for noisy data, it can sometimes find very different clusters. So the question becomes, how do we know what the best cluster is? There are many ways of doing this, such as mutual information or da-da-da-da-da. But one really easy way to do it is just finding the lowest average distance from each point to its centroid and taking that assignment. So for instance, in this one, let's say the average for this guy is 2, average for this guy is 1, average for this guy is 3 distance. Euclidean distance, simple Euclidean distance. Then the average is going to be 2 distance units away from their centroid on average. And this would be a much better clustering assignment than one that had an average point to centroid distance of, say, 4 or 5, because clearly this is a very good assignment and all these centroids very well fit its points. So that's kind of how k-mean works. And we're actually going to look at a little video now just to explicate it some. So you can see here what we're actually doing is that we have these several points here that are being declared. In fact, 5. So we have 1, 2, 3, 4, 5 points that are being initially randomly chosen. From these, we're going to find the closest instances for each one of these points. After we find the closest instances, we're going to calculate the mean, then reassign the closest instances based on those new means. We're going to keep doing that until no instances change, and you'll see that pretty quick here. Look at that. And you'll see at a certain point, no clusters change, even though none of these really look like they have that distinctive clustering patterns. And again, this is just because k-means is guaranteed to converge. So here we just keep going with any number of different data points, any number of different groups. I'll let you look at this video online. It's the k-means clustering example video. It's pretty easy to find if you're interested. But for now, we're going to jump into dimensionality reduction. So dimensionality reduction is a pretty simple and explanatory name. It just seeks to reduce dimension. So here, if we were to look on our left figure, we would see a 3D helix shape of some sort of data. Now, when we want to reduce this data, clearly there's some pattern here in the colors, right? And clearly, if we were to say travel along this coloring, the red should be very far away from the blue. And as you can see, the dimensionality reduction here accomplishes that. And that's pretty much our goal, I guess, honestly, just to keep as much information about the original space as possible in our newly reduced space. And how we're going to be doing that is to reduce dimension via projection. Now, projection is essentially taking a line from one of these points to that axis. So here, if we draw a point from every point here in this red data cloud to this axis right here, we're going to get a triangular shape. If we do the same thing for this axis below, we're going to get a circular shape. And if we do the same thing for this axis here, we're going to get a rectangular shape. And again, this is just projecting the data onto any number of these different axes. And the question now, I think that everyone's probably wondering, is that how do we actually know which projection is the best for this data if we wanted to take it from 3D to 2D? We'll talk a little bit about one method for it here in a second or two. But the biggest thing about dimensionality reduction is that we just want to preserve certain properties in lower dimensional space. Kind of how I mentioned before, there is clearly some local information going on through this structure, even though if we were to just say cluster these together, then like reduce them, or if we were just to do a projection-based dimensionality reduction like we're doing here, this information that's encoded here by color would not be retained at all. And so this is where something we call manifold learning actually comes out, where we essentially learn or seek to learn the shape that this data could fit onto very well, and then project that into lower space. And this link down here, the science link, that will actually bring you to the paper where this is originally called. It's called manifold learning if you're interested in looking into it more. And this is actually going to preserve this certain property, the helix shape, in lower dimensional space. And so again, I kind of mentioned here, okay, so now we're just seeking to preserve some property, you know. What property are we looking to preserve in this example? What are we really looking to preserve? Well, we're looking to preserve variance oftentimes. And so here, this is actually the idea of principal component analysis. So principal component analysis is going to try to find the vectors that best preserve the variance in the data, and then try to find as many of those as you want. And so the idea here is if we look at our first principal component, we are actually going to find the very, very first vector that if we were to project our other data onto it, it would be the most variance would be preserved. And so it's pretty clear that along this line here, if we were to take, and obviously we have to extend it out a little bit, but if we were to take any data point and draw it onto this, there would be a lot of variability in the data projected onto that still. However, if we were to say take a line like this, right, then clearly a lot of these data points collapse very, very close to each other or on top of each other on that vector. Now you may be saying, okay, I understand the first principal component, we're just finding the best vector that maintains variability. What's going on with our second principal component down here? You just said that was the worst. Well, the reason the second principal component looks like this is because there needs to be a component of orthogonality. This needs to form a right angle with our first principal component. And then, with that constraint, then we need to find the vector which preserves variance the best. Now basically what that constrains us to doing at this point is taking this and rotating it around our PC, our first principal component, and then finding whichever one of those actually maximizes the variance on the projected data. And actually we find it's just this one right here. And so we project our data again, just straight onto this. And that's what our second principal component, and that's how our principal component is going to be reducing the dimension of this data. And when we actually take and plot this data now in two-dimensional space with our two vectors that we found here, we can actually see that it retains a significant amount of the information from this three-dimensional space. In fact, it just looks, honestly, like the same exact data pattern except in two-dimensional space. And that's what we're going for. And we're especially going for this when it's not just 3 dimensions to 2 dimensions, but much more so when it's, say, 40 dimensions or 100 dimensions to 2 dimensions. At that point, we want to maintain as much information about the original data and its structure in very low dimensional space. And this is kind of the goal of principal components. So next we'll actually take a look at the code. So I've distributed this code out to everyone, I think. I've also distributed out the data file that was needed. That was not the file I wanted to go into. And so here, you can see that in my directory, I have the crimecommunity.csv dataset, and I have the intro AI ML basics.py file. And so you'll need to have these two in the same directory. And for the imports, you will need to probably install TensorFlow, and you will certainly need to install TensorFlow probability for this to work. Before you run this, just run those 2 commands that I've put in here. That should install into your environments TensorFlow. If you want to use a virtual environment, please feel free. I've just installed it onto my system because it's easier. And I'll just kind of start going through the code. So basically, this is going to be importing some of the models we'll be using. It's going to be importing the metric we'll be using, and then we'll also be importing NumPy and matplotlib for plotting. So what we're going to start with is importing and pre-processing our data. So here we're going to be loading in the crime data set, which I've called crime. Oh, whoops, sorry about that. Have to keep that in there. Perfect. So we're going to call this dataset crime, and we're going to take 75% of it and use it as training data. I've called that %train. Now we're going to split our data into the sample and the label just a quick explanation of what this does. This says keep all the rows, take the 0th column, including the 0th column, which is what this comma does, and go all the way to the second to last column. Now, the reason we're only going to the second to last column on this particular data set is that the last 2 columns are the labels. The second to last is the continuous label. The last one is the binarized label. And so we're just going to go to the second to last column. These are going to be all of our features, which comprise our sample. Again, our label here, the binary label, is only the last column. The continuous label is the second to last column. We want to use the binary label for this this exercise, so we're just going to go crime to the -1th column, and we're going to include that one only. That's what this comma does. If you don't understand that, don't worry too much. It's done here for you. If you're interested in doing this more, the machine learning class will do a lot more of this. Next, we're going to get our training indexes. These are just going to be randomly chosen instances from the training set, and then these are, or for the training set, I apologize. And then the testing indexes are going to be the rest of the indexes that weren't used for training. So basically, we're just taking 75% of the instances and 25% of the instances, and we're going to be using those for training and testing respectively. Here, we're just taking those, pretty easy. And actually here, through our variable explorer, this is where this kind of program becomes really nice, because we can start to see that our whole crime data set is 1993 by 102. We can see that our sample only has 100 columns, which is good because we should only have 100 features. And we can actually also see that sample test is 25% of the data and sample train is 75% of the data. Additionally, our our label is the same dimension as our sample. So these are really, really nice to keep in mind, because if you do have an error with how you're collecting your data, how you're splitting your data, this is where you can find it very quickly. Okay, so let's kind of get into the actual machine learning stuff. So we're going to start with just a simple linear regression model. So what we're going to be starting with is an sklearn linear regression model. And so again, this is where we import that as sklearn.linear model. And we're going to declare a linear regression model. We're going to fit the linear regression model against sample train and the label train, because remember, linear regression is a supervised machine learning task, and so it has to know all the information and also know the answers so it can train itself against those answers. Then we're going to make a prediction with our line. So basically we're going to take each one of these sample test instances and we're going to say, okay, linear regression, what do you think this should result in? Then, because linear regression is a regression task, remember it's going to spit out some continuous number like 0.5, 0.76, whatever it is. We actually need to binarize this. We need to make it a 0 or 1, because again, our label is a 0 or 1. Is it a high crime community or is it a low crime community, essentially? And so what we're going to do is we're going to say, okay, in our predictions, find where the prediction is less than 0.5, and we just have to get that out with the 0, and then just set that equal to 0. So what this is doing is this is going to be thresholding our prediction vector to 0s and 1s based at the threshold of 0.5. So if it's bigger than 0.5, we're going to say it's 1. If it's less than 0.5, we're going to say it's 0. Finally, we're going to test the accuracy and print it out. So let's just take a look at this guy. And I'm just using Control-Enter to do these, or Command-Enter for a Mac. And you can see that our linear regression accuracy is actually 0.899 for this particular data set, which is pretty good. It's a very simple model, it's a very simple threshold, and it's very, very fast. I mean, I ran that on my Mac while recording this video in less than 2 seconds. So it's a very quick model, and it did very well. So for a lot of problems, linear regression will work. A lot of problems, simple models will work. You don't need to throw deep learning at it. But, you know, that kind of gets into the whole machine learning theory of things. What I want you guys to take away from this is that this is just the way to do basic sklearn modeling. And the reason we're using sklearn as opposed to, say, TensorFlow for some of these basic models is that it's very, very simple to do this in sklearn. It's very, very easy to go experiment with data sets and different models and da-da-da-da-da. Whereas with TensorFlow, it's very built around being very customizable, which is great, but for these linear models, it's very, very complex and unnecessarily so. And so we're just going to be using sklearn for some of the basic stuff. So next, we're actually going to be doing PCA, and then we're actually going to be manually projecting the data onto the new axes for visualization. So here in PCA, we're going to use PCA with two components. We're going to be looking for those two axes we're going to be projecting on. We're going to fit our whole sample on this. Now, because this is not necessarily a supervised task, this is an unsupervised task, PCA doesn't care about the label. We're just going to do the whole sample. We just want to visualize the whole data set in this example. We can actually just train this on the sample training and then evaluate it on the testing and see how accurate it was and all sorts of things. But for this example, we just want to visualize our data. So we're going to fit it against our sample. We're going to get our principal components out, and this is the way you do that in sklearn. And again, at the bottom, I don't know if I've mentioned this, at the bottom there is the documentation for all of these methods. So if you're confused about where the magical components underscore is coming from, go take a look at the documentation. The sklearn documentation is fantastic, and I think it'll help a lot. And then what we're going to do is we're going to say our projected data is our sample dot product with our principal components. So essentially, let's just run this real quick so I can show you some dimensions. It's not defined. There we go. So here, oh, here we go, pcoms. So here we're actually finding a p by number of components we want vector, and then for our sample, where's our sample? Here we go. We have P here. So basically what we're going to be doing for this matrix multiplication is 1993 by 100 times 100 by 2. And this gives us a 1993, that's how many instances or communities we have, by 2, that's how many features we have now, representation of the data, and we can actually visualize this now. So let's take a look at what that will actually look like. So this is actually what our PCA 2D projected data looks like. Now, I think a few of you have taken the some statistics courses like multivariate analysis and stuff that actually goes into how you can interpret PC scores. For our purposes, we're not too worried about interpreting the PC 1 and 2 scores. We're more so interested about the general shape. And as you can see, there's not a whole lot of general shape right now that we can see. Maybe some of the statistics people in here will say, oh, maybe that's a log transform or da-da-da-da-da. You're more than welcome to do that, to try it, but this is just an interesting way to visualize data, and we actually use this for higher dimensional visualizations and other methods, which we'll start seeing right now. So let me run this command, which just clears the figure out. Okay, and now we're going to be doing some k-means clustering. So we're going to be doing some clustering on all the data, and then we're going to visualize the data. So here we're doing k-means with 2 clusters. We're going to fit our sample. Again, we don't care right now about sample train, sample test. We can do that stuff if we were interested, but right now we're just interested to see how many groups or clusters there are in the whole sample. And this n clusters is just a hyperparameter that we have to play with. So feel free to vary this and see how it ends up changing the results. So we're just going to be fitting on the whole sample. And then we're going to find the assignments for this. So this is going to be k-means.labels underscore. If you're curious what this underscore is, it's basically shorthand in Python for don't use this. It's an internal variable. We ignore that. We don't care. We want those. And we're going to be looking for the centers of those clusters, getting the cluster centers. And we're going to just run that real quick now. Perfect. And now, again, we run into this problem where we can't plot 100-dimensional data. So we're just going to use the PCA vectors that we found instead. So what we're going to do is we're going to project our cluster centers in the same way we projected our sample. We're going to declare a color map just for some ease of use. You're more than welcome to change these colors to your heart's desire. I had them as red and green for the holidays for a while. And then we're going to make a scatter plot with this. Now again, we're actually going to be plotting the projected data here, but we're going to use the color map based on the assignments that our k-means clusters thinks we should use. So when I run this, we're going to see not only the projected data with colors based on the assignments, we're also going to see the projected centers in these pluses. And let's look at that real quick. Perfect. So here you can see that with two clusters, k-means actually finds that basically the left side of this data should be yellow, and the cluster center is going to be right here at about 0, 1. Alternatively, the orange clusters is the right half, and we just have another center there, and it's just kind of interesting to see where the cluster centers end up, in my opinion. If we actually change this to 4, we can see how this begins to change as well. So if I just do this whole chunk of code here, oh, dang. Okay, well, we can do that another day. Yeah, no worries. Okay, moving on. Next, we're actually going to be using a basic neural network to classify the crime data. Now, this is just going to be a feed-forward neural network, and I'm not sure how much you guys have talked about neural networks or anything like that, but the idea here is that we have fully connected layers connecting 8 nodes to 4 nodes to 1. Now the idea here is that we have 8 weights essentially. So from all our data, we're all connected to these 8 weights. And as soon as we have these 8 weights, then those 8 weights all connect to 4 weights. And this is called our hidden, these are 2 hidden layers here. Now these 2 hidden layers are going to be doing the magic of the neural network with these activation functions. These activation functions are introducing nonlinearity into our predictions, and this actually kind of provides a lot of the power of the neural network. And then we're ending with a 1 layer. Now the reason we're at a 1 layer and not like a 2 or a 4 or whatever layer is because we just want a 0 or a 1 at the very end to determine if it's a high crime or a low crime instance. This is going to be using the keras part of TensorFlow. This is just kind of a nice front end for the TensorFlow API. You're more than welcome to use the TensorFlow API, but it is significantly more difficult, and keras provides a tremendous amount of usefulness, just so much easier than the full TensorFlow does. Next, we're going to compile it, use a specific optimizer, This you can pretty much just leave it the same. If you need to change the metric from accuracy to, I think it's mean squared error for continuous, or for regression tasks, you may need to do that. And then we're just going to fit the model on our training data and our training labels. And we're actually going to update this 50 times. That's how many times we're going to be training this neural network. Then we'll print out how accurate it was. So let's try this guy out. And you'll see this will actually take a little bit longer because we have to train it for 50 times. Alright, perfect. And you can see our accuracy of 0.9056. So I'd like to contrast this in terms of the linear regression results. If you remember, it's 0.899 accuracy for the linear regression model. And this is actually one of the big criticisms of deep learning. It's a lot of work for not always a lot of results. But I will say, this is a very, very small data set. Were this a very large data set, we would begin to see the accuracy of neural nets really outpace linear regression. So if you're interested in neural networks or anything like that, I think the electrical engineering department has a very good class that just talks about neural nets. The machine learning class also does discuss neural nets, but not as rigorously as it does some of the statistical machine learning methods. So next, we're going to jump into something you are all very familiar with, hidden Markov models, actually. So we're just going to call TFD our distributions library. And here is something that I've set up as this goofy little example. So we're going to be assuming that a hidden Markov model has hidden future states and only a known current state, you know, that as hidden Markov models work. And we assume we want to model a casual exerciser's run. Now, emphasis on the casual. We assume a categorical 0, 1, 2 distribution, where 0 is walking, 1 is going to be jogging, and 2 is running. And here, what we're saying is that most of the time he's running, 60%, sometimes he's walking, sometimes he's running. Pretty casual runner. So we're assuming that walking then generally results in jogging or running in the next step, and this is going to be our first vector here. So here, if we're walking, this very first vector is the walking next step vector. We're going to assume most of the time we're jogging with 70% likelihood, or running sometimes with 20% likelihood. Sometimes we're just tired. We just want to run. We just want to walk. We just want to keep walking. 10% likelihood. Jogging usually results in more jogging in the next step. And here, this is our jogging next step probability vector. And so here you can see with 60% of the time we're going to keep jogging, 30% of the time we get tired and just start walking, and 10% of the time we really get motivated and go run. And running normally results in walking in the next step. So here, this is the running next step probability vector. Here, if we've run in the last step, then the next step is probably walking 80% of the time. Sometimes we'll just regress to jogging 15% of the time. And man, sometimes we're just feeling it. 5% of the time we'll keep running. So we're going to run these two guys. Perfect. And then we're going to assume, I made a mistake here, this should be normal. So we're going to assume walking is a normal 2-1 distribution, jogging is a normal 5-3 distribution, and running is a normal 9-0.5 distribution. So what these are the means and the standard deviations of our normal distributions. The idea here is that walking is normally at 2 miles per hour with a standard deviation of 1. Jogging is normally at 5 miles per hour with a standard deviation of 3, meaning we're not very good joggers. And running is normally at 9. When we're running, but from these probabilities, we don't run for very long. All right, and now we're going to put in our observed distribution. So this is just going to be these numbers right here, these distributions, codified for our observation distribution. So now what we're going to do is we're actually going to take this model and run it for 7 steps. Now that we've run it for 7 steps, let's find the mean of the runner for the workout at each of the 7 time steps. So you can see here that we actually have a tensor that consists of the mean of the runner at all 7 time steps. So at the very beginning, our average speed is about 5.2 miles per hour. Because we're kind of lazy, we get back to 4.3 miles per hour in the next step. The next step, the average goes up, and you can see how the average evolves over these 7 time steps. And I actually encourage you to mess around with the number of time steps and just see how the model acts and converges. But next, we actually want to find the probability that the runner was running at, another error, was running at 4 miles per hour in this case. So we're going to do that, which is get the model's probability of 4. I'm just going to print that and find that the probability of running 4 miles per hour is about 8%. Now, what does this PDF that our hidden Markov model has generated, what does it actually look like? Let's see what we're running like. And you can see here that our biggest peak is at 2.5 miles per hour right here. And this is the density. For anyone who knows that, that's great. If you don't know that, that's okay. Basically, this is just how often it happens. So you can see most often our speed is 2.5 miles per hour. And this is actually interestingly bimodal because we have a second mode or second peak here at about 9 miles per hour. Now the reason that is because of our initial distributions here. These guys are right here. So you can see that jogging and walking are somewhat indistinguishable, and in fact 5 doesn't really have a peak because 3 is such a large standard deviation. Most of our speeds through this range, jogging and walking, are homogenized to about 2.5 miles per hour. However, it does make sense to have a second mode because there is a very distinct state, which is running, where we're running 9 miles per hour and we're very, very much running at that point. So you can see here, this is basically saying that we're either walking, jogging, doing something, or we're really running. So that's essentially a very, very easy way to make a hidden Markov model. And I actually encourage you to look through a lot more of the TFP distributions library. It has a ton of different distributions and probability stuff in there. Here are all the documentation notes that were, for all the methods that were used throughout this. I have the matplotlib pyplot library docs. I have the scatter docs. This is all pretty useful if you kind of struggle to understand almost any of this. But for the most part, I think the assignment that's coming should mostly just be fit, prediction, stuff like that, and then play with some hyperparameters. If you are interested in moving forward, playing around with some of the underworkings, hit those documentation links, because they'll show you things like getting the components out of the principal components, getting the labels out of the k-means assignments and stuff like that. And that's pretty much all there is to coding at this point for machine learning. Feel free to send us questions if you have any. If you're having problems running the code, please give me a holler. Otherwise, thank you all for listening.